So how did you go with finding the total different number of combinations that existed with the number of cupcakes and number of cookies that we could buy that used our entire $10 budget? Well, there are a total of 11 combinations, and I've summarised these combinations in the table just up here. And what I'm going to do here today is I'm actually going to graph these combinations, where I'm going to let X represent the number of cupcakes, and I'm going to let Y represent the number of cookies. So I'm going to go ahead and graph these combinations. So what this graph now shows us is a visual representation of the combinations that exist of the number of cookies and the number of cupcakes that we can get to use our entire $10 budget. But there's more points that do exist on this graph, and we give these points special names. The first type of points I want to look at are the points that are actually on our line here, our line of best fit. These pink dots represent what we call feasible solutions. Now, feasible solutions are solutions that exist that work in context of the problem. So, for example, we can have 6 cupcakes and 35 cookies. That is a combination that will fit within our budget. But feasible solutions aren't restricted to just using the entirety of our budget. We don't actually have to use the entire budget. So feasible solutions also exist inside of here, where we've got, say, 30 cookies and 6 cupcakes, or 25 cookies and 7 cupcakes. So feasible solutions are solutions that we can use in our problem. The other type of solution that exists are what we call infeasible solutions. Now, infeasible solutions are combinations that don't fit within the context of the problem. So in this, they don't meet our $10 budget. So an example of this would be, say here, at 60 cookies and 7 cupcakes. There is no way that we can purchase within our $10 that amount of cookies and cupcakes. So infeasible solutions are combinations that don't fit the context or the constraints of our problem. Now, when we start talking about feasible and infeasible solutions, there's actually a special region to this graph, and it's this region right here. It is what we call the feasible region. Now, we define the feasible region to be all the combinations that exist that meet the constraints of our problem. Now in here, we've got a $10 budget, and we're looking at how many different cupcakes and cookies could we make for that $10. Now, there's going to be some boundaries that exist here. Obviously, the first boundary is defined by the amount of money that we've got. But the other boundaries that exist that we haven't talked about are the physical number of cookies you can make. Now, within graphs, they do have negative sections of the graph, but you can't produce a negative number of cookies or a negative number of cupcakes. So the other boundaries that exist are here along the x-axis and here along the y-axis. Now, there are a couple of other words that you might hear and you need to get to know when we start talking about the feasible region. And the first one is this: the simplex. Now, the simplex is looking at what combinations exist within our feasible region. In other words, it's another way that we can define our feasible region or refer to our feasible region. And the second word is this: the vertex. Now, the vertex is where the boundaries of our feasible region meet. So all the points where the boundaries of the feasible region or the simplex come together. So in this case, the boundaries meet along the x and y intercept or the origin. They meet up here at the y-intercept, and they also meet over here at the x-intercept. So this graph here has 3 vertexes, which are where the boundaries of our simplex or the feasible region meet. So that summarizes what the feasible region is and how we graph the feasible region. In the next video, we're going to have a look at how we define our feasible region algebraically.